everybody, it's Miss Peachy from your WCA Physics class, and today I'm doing a video tutorial to go through your first portfolio for semester B. This is your sound lab portfolio. So it's a fairly easy lab for you guys to do. I just wanted to kind of explain a little bit about the format and especially kind of how to do or how to use the simulation, the online sim. It can be a bit tricky. So first of all, here I am in your lesson viewer. And the very first thing you always need to do for your portfolio is you're going to be doing a hypothetical experiment. I wanted to remind you as I go to my website, I'll bring that over to show you. On my website, there's always going to be, let's kind of move over here a little bit. It's going to be a video. This is actually the older one that I had that I'm redoing because this wasn't done super well. Explaining how to do the portfolio, but there's also going to be a copy of the lab rubric. And so this is what you're going to need to use as a format for all of your labs here. Same one you guys used for first semester. So I'll pop that out here in Google Docs. Know that you can download this into Word. You don't have to include it into your write-up. It is actually nice if you do. I do kind of like you guys to copy and paste this at the beginning of your portfolio. But if you don't, I always put it in there as well. So that first section is the introduction/hypothetical. And in this part of the portfolio, you will introduce the concepts that we are covering in this portfolio and what you're testing for. And then you need to devise a hypothetical lab that you could do if, for example, you needed to do something at home that would kind of test for or experiment with the same concepts. So in this hypothetical, you're going to talk about what materials you would use, what would you measure, what would your results be, what would you expect the results to be, and what would it indicate if the results that you came up with were different than your expectations? A lot of times students will put that if there were results were different, there was some sort of error, and they often say, well, that error is probably some sort of human error. And I really want you guys to get away from saying human error because, you know, of course there's a lot of potential for human error. But we want to be very specific here with what human error actually is. So where could you have gone wrong? Assuming that your initial understanding was correct and what you were testing for was based on theory that was from the text, then what could you have done wrong in this situation? Oftentimes these are things like maybe you didn't have a very good setup. Maybe there's something wrong with the way you put your equipment together. It was not testing what it was supposed to be testing, or it malfunctioned or something like that. Maybe there was something wrong with your measurements. Maybe you were inaccurate with your measurements, that kind of thing. Maybe you had some calculation errors. That could also happen. Sometimes we notice errors in rounding or in calculating. Going back to that setup, and you'll see this with the lab I'm going to show you here. There's oftentimes error in just like reaction time and things like that can introduce error, especially if you're timing something, which is what we're going to be doing in this portfolio. So make sure you're very specific with what those errors actually are, okay? So once you have that part, the hypothetical, you're going to make a hypothesis of what you think is going to happen in this experiment, this online lab that you'll be doing. Okay, so your hypothesis should indicate how does the frequency of sound affect the speed of sound? Do you think it does or doesn't, and why? And do you think the amplitude of sound affects the speed of sound, and why? Including, and I always put this here, let's see if I have it on here. I want you to use text-based evidence for your hypothesis. So use your text to find information to support your hypothesis. According to the textbook, cite the pages that you found the information on. Cite some information from the textbook to support your hypothesis of whether or not amplitude or frequency affects the speed of sound and why. Okay? That being said, you're going to look at two different methods to measure the speed of sound in air, and we're going to evaluate these. You're going to be using this lab. It's using a program called PHET, P-H-E-T. We've done quite a few simulations through PHET this year. They're a really awesome website that provides free simulations for science of all different genres. And we're doing the sound one. When you do open that up, it is a Java program. Okay, so it starts off like this. Looks a little different than the one in the lesson where it has some dude here. All right, sorry about that. So here we have, obviously there's a guy on this one. There's a lady on this one, so it's an updated version from what they have in a screen capture in our lesson. So you're going to actually be using, at the top here, where it says measure. We'll be clicking on that one. And when you do click on measure, let's try that again. Okay, I'm going to close out of it and reopen it because sometimes there's like a little glitch here. It's still going. Alright, sorry about that. What happens is this little box here with the timer, you can click and drag it around, and I had used this earlier, so it was on my other monitor. It was just kind of sitting there all by itself. I was like, where'd the timer go? Oh, it's right over there, so I just had to drag it back over here. Anyways, so you'll have a timer. You'll have a speaker. There's a ruler. I'm going to bring this over just a little bit so you can see the other part of this. You'll have this button that says clear wave, and you have a play and a pause over here too. So what you're going to be doing is, I'm actually going to click this and drag it down to the bottom so that it's right next to the play and pause button. It helps. First thing you're going to do is I'm going to clear the wave, and I'm going to take these. There's two blue lines right here. I'm going to click and drag these so that one of the blue lines I'll put at the very top of this, like the very end of the speaker, and that's where I'm going to put my 0 mark for my ruler as well. And then my other blue line, if I can catch it, sometimes it's kind of a pain to try to catch it for some reason. I'm going to click and drag it to the exactly the 5 meter mark. This allows me to more easily eyeball, the waves themselves. All right. Okay. So, one of the things I'm going to be doing is I want to look at the time it takes for a wave to travel 5 meters. Right? So I'm actually going to look at, using my stopwatch, the time it takes for the wave to go from here to here. I'll start and stop the stopwatch, and I'll be able to get a time for that. Because distance divided by time is one way to calculate the velocity of the wave, right? The other way to calculate the velocity of the wave is frequency times wavelength. Frequency times wavelength. So if I can figure out the wavelength, then I can determine the velocity by taking the frequency, which is listed over here, 500 hertz, and multiplying it times the wavelength. Okay, so 2 different ways to determine the velocity of a wave. Okay, so you guys can see that we'll be calculating the wavelength here, which is the Greek letter lambda, by taking the number of wavelengths that we can count divided by the distance of 5 meters. And that should give us the length of one wave. Okay, so wavelength divided by 5 meters. Okay, so when we do that, I'm just looking at that, making sure I was right. Let me just play this for you one time and kind of give you an idea of what it looks like. Okay, so I'm just going to play this and kind of look at it, right? And I want you to notice what it looks like. I'm just going to start it and then I'll pause it. Okay, and I kind of stopped it a little too late, so you may have to play with that a little bit. But every one of these, get a little closer to the computer, each area of dark and light together is one wave. So if you can see here, that's 1, 2, 3, 4, 5, 6, 7, 7.5-ish. But I went a little too far because I went over that 5 meter mark. Right, so I can clear that wave, I can start over. And again, I can play it and try to pause it is the second it reaches there. Pretty good that time. So again, 1, 2, 3, 4. Kind of makes my eyeballs buggy. Try it again. 1, 2, 3, 4, 5, 6, 7, 7.5. It's very similar to what I had before. So I would take that. That's the number of wavelengths. So divided by, so in 5 meters I have 7.5 wavelengths. So I would take take 5 divided by 7.5 to get a wavelength of about 0.67 meters. It's about one wavelength. And then frequency of 500 hertz times 0.67 gives me the velocity of the wave. Does that make sense? So that's one way. And the other way is taking the total distance, 5 meters, distance divided by time, which we'll be calculating shortly. And that's the second way of getting the velocity of the wave. Okay, so to get the time, this is the tricky part. This took me 3 years to figure out. So I did this video once before, and I just figured out the way to do it now, because before it was all messed up. All right, so it's weird, because you have to play. When you push play, the wave starts to go, right? And when you push pause, the wave stops. But in order to time the wave, you'd pretty much have to push play and start the timer simultaneously, which you can't really do on a computer. But I just figured this part out. If I push start on the timer, it doesn't start moving. The timer doesn't start ticking until I push play. So I can push play, and then it's the second the wave hits the 5 meter mark, push pause, and it'll tell me the time. This is even better. If I push this button here, this is a step button, it's not a pause button. I just push it little by little, let the wave come out. The second that first area of rarefaction hits the blue line, stop it. There's my time, 0.0153. I have gone over a little bit, but that's my time, right? Cool. Got to clear the wave, stop this, and reset it to start over. So let's try that one more time. Start the timer, step it. I'm trying to get there eventually. Alright. Right there, 0.0151. Pretty decent, pretty close to what I had before. So that's how you're going to get the time. So again, then distance, 5 meters, divided by 0.0151 seconds gives me velocity of a wave. So that's the two ways that you can calculate the velocity of a wave. Okay, so what you guys are going to be doing is you're going to be doing the same procedure for 6 different frequencies. So your data table is going to have 6 different trials, 6 different frequencies, and you're going to be calculating the velocity at those frequencies for both those techniques, both those different ways in which you calculate it, both using d over t, or distance divided by time, and wavelength times frequency. So make sure that you have the data table complete, but also to get full points for this, ladies and gentlemen, make sure you're also, let's see if I can get back to it here. Make sure you're also showing me your calculations. So there's a whole section on analysis. It's 5 points. And you need to show me all the calculations that you're doing. So you're listing all the distances, all the times, showing d times t equals, I know it's maybe a little bit tedious, but I need to see all those calculations. It helps me to know that you know what you're doing, but it also helps me to see where you went wrong if you have mistakes. And while these calculations are pretty straightforward, you guys will agree with me that at different times in different labs, those calculations are sometimes more complex. And so it helps me to see, where you made mistakes. So it's a very important part of the learning process. And then finally, you're going to answer the conclusion questions that are found at the end of the lab here, okay? Let's see if I can get to that. So, laboratory conclusions, evaluating, use Appendix F of your textbook. Identify a medium the sound could have been moving through in this virtual lab. So look at the Appendix F and see the speed of sound through different substances and see, what it could have possibly been moving through. And which method do you think is more accurate? Why or why not? You may want to think of those sources of error as well. And based on your results, is the speed of sound in air the same for all sounds, or do some move quickly or more slowly than other sounds? Explain, okay? So that's pretty much all you need to do for this portfolio. If you guys have any additional questions or concerns, you could call me at extension 2204 or send me a webmail message. Have a great day.